This video is going to introduce what's called L'Hopital's rule. It's a way to evaluate an indeterminate limit, and we'll get to that in a little bit. And I'm sorry I can't be with you in the classroom because I always like introducing this and watching your faces. And I could have shown you this at the beginning of the school year, but it's so nice. I didn't want you guys to be overusing it at the time. But you're going to love it. It's a real nice way to evaluate limits. So what I have here on the paper are just some prior limits that we've solved in class, and I'll also post some prior videos on evaluating these limits. But for the time being, just take a look at these. We've gone over these in class, and I'll repost the video series on this so you can go back and check it out as well. So here's some limits that we've solved and the solutions to them. I'm not going to go into detail about how to do that because they're in my prior videos. You can go back and take a look at that. Okay, so there's a few. And here's a couple more that we've gone through. And even D, we've talked about different ways to evaluate that limit. And then so here is the situation of evaluating limits at infinity, and we'll come back to that as well. Okay, and if you need to pause the video or rewind it, that's the nice thing about technology. You can always go back and take a look at that. Here are some examples of using the definition of the derivative to figure out what the limit is. All right, so like on this one, we could say what's the function that's being used here on the definition of the derivative, and the function is y equals x squared, and the derivative's being evaluated at 3. So we can think, all right, well, the derivative of x squared is 2x, and if we're evaluating that at 3, 2 times 3 is 6. Same thing goes on these last two here. This is definition of the derivative in disguise because this is the sine of theta minus 0, and down here being theta. So the function being used here is the y equals the sine of theta. The derivative of the sine of theta is the cosine theta, and if we evaluate that at 0, we get 1. And this is the definition of the derivative of the cosine function. So if we take the derivative of the cosine function, we get the opposite of the sine function, so negative sine theta, and if we evaluate that at 0, we get 0. Okay. So here's L'Hopital's rule. And notice in red there, it's only for limits in their indeterminate form. And there's different indeterminate forms, but the two we're going to focus on here, and you don't have to worry about the other ones. You can look them up if you want. But 0 over 0 is indeterminate, as well as infinity over infinity. So if we have a limit in its indeterminate form, we can take the derivative of each individual function and try to reevaluate that. Notice this is not the quotient rule. We're just analyzing the ratio of two different functions, and we're analyzing the ratio of the slopes of two different functions. And if this is still indeterminate, we'll move on to the next one. So all we're going to do here is go back through a lot of these examples and just show you how you can use L'Hopital's rule to solve all of these. First of all, this one, can't use L'Hopital's rule on this because it is not indeterminate. If we plug a 2 in here, we get 4, 8, 9 over 4, 12, so 16 minus 4 is 12. And notice that's not indeterminate. That's not 0 over 0. It's not infinity over infinity. That's 3/4. So L'Hopital's rule is not possible on this first one. Look at the next one though. If we plug in 0 for x here and here, plug in a 0, we get 8 minus 8 over, plug in a 0 there, 0 over 0. So in my video prior, we expanded this binomial and simplified it and got 12. Now let's just use L'Hopital's rule. It's indeterminate, so the value of this limit is going to be the same as the value of the ratio of the derivative of this function. So let's see the derivative of this, chain rule, times the derivative of that, which is 1, minus 0, so I'm not going to write that, over 1. Now let's try and redetermine the value of this limit. Plug in a 0 now. Plug in a 0 here, 2 plus 0. 2 squared is 4. 4 times 3, 12 over 1, which is 12. A lot faster than what we did at the beginning of the school year. Next one. The beginning of the school year, well, first of all, let's plug in negative 4. 16 minus 20, negative 4. Negative 4 plus 4 is 0. Plug in a negative 4 here. 16 minus 12 is 4 minus 4, 0. So notice indeterminate. At the beginning of the year, we factored, simplified, and solved. Now let's just use L'Hopital's rule. So the value of this indeterminate limit is going to be the same as the ratio of the slopes of these two. So let's say the derivative of this one is 2x plus 5. Derivative of this one is 2x plus 3. And if we now plug in a negative 4, we get negative 8 plus 5, which is negative 3, over negative 8 plus 3, which is negative 5, equals 3/5. Nice and fast. So what you're going to have to do here, you love L'Hopital's rule. I think you can see it's nice already. You have to be careful not to overuse it. You always have to check for indeterminate first. 0 over 0 or infinity over infinity. Here's another one. So let's check for indeterminate first. Plug in a 9. 81 minus 81. Numerator is 0. Plug in a 9. The square root of 9 is 3 minus 3 is 0. Indeterminate. Okay, so we can use L'Hopital's rule. So let's take the derivative of the top function there. So that's going to be 2x. Derivative of the bottom function here, that's 0. Derivative of the square root of x is 1 over 2 radical x. So if we simplify that, we get, what, 4x over 1, 4x radical x. So let's try to reevaluate that now. Plug in a 9, and we get 36, plug in a 9 there, 36, square root of 9, 36 times 3, which is 108. Same as what we got there. Okay. Notice the next few, well, the next 3 here, we cannot use L'Hopital's rule there because we don't, if we plug in a 0, we don't have 0 over 0 or infinity over infinity. So that's not going to work on these. We have to look at those conceptually and understand those. Okay. Look at F though. If we plug in infinity, we have 1 minus infinity squared. So that's basically negative infinity on the top. And plug in infinity here, which would be infinity minus 7, which is infinity. So that is an indeterminate form for that limit. So we can use L'Hopital's rule. So let's take the derivative of the top, which is going to be negative 1 minus 2x, and the derivative of the bottom, which is 4x. And now let's plug in infinity. Notice when we do that, we get an indeterminate form again, which is, in this case, negative infinity over positive infinity. So what do we do here? It's indeterminate, so we can use L'Hopital's rule again. Take the derivative of the numerator, take the derivative of the denominator, and now let's reevaluate that limit, and we see that it's negative 1/2, just like we found over here when we did that earlier in the year. Last couple. Instead of using our shortcuts with the definition of the derivative, notice when we plug in a 0, we get 9 minus 9. Plug in a 0, 0, so that's indeterminate. So we don't have to expand this binomial. We can use L'Hopital's rule. So let's see. Okay, derivative of the top, derivative of the bottom. Remember, this is not the quotient rule, so be careful of that. Be careful of overusing this rule because students, when they first learn something, will a lot of times do that. So let's plug in a 0 now, so see what we get. 3 times 2, 6 over 1, which is 6. Got it. This one, plug in a 0, sine of 0 is 0 over 0 over 0, indeterminate. Let's use L'Hopital's rule. Derivative of the top, derivative of the bottom. Cosine of 0 is 1, 1 over 1. This one, plug in a 0, we get 1 minus 1 over 0, which is indeterminate. Let's use L'Hopital's rule. A derivative of the cosine is the opposite of the sine function over 1. And so negative sine of 0, plug that in, we get 0. All right, guys, time to practice.